Hello, this is video 10 in the PETTaLS version 1.7 video tutorial series. PETTaLS is the application that I wrote, the pretty good exciter and tactile transducer loudspeaker simulator that you can use to simulate and design loudspeakers using exciters attached to surfaces and plates that are, in the case of my program, rectangular shaped. So that could be a window or a piece of cardboard or a big piece of metal or something, or wood, or maybe drywall even. Lots of different things. So I, in this video, am going to be talking about the impedance window, which is over here. This is the 10th video, so if this is randomly appearing for you on your feed and you have an interest in this, you should probably go watch the other videos first because you're going to be missing a lot of context. So there are three tabs here: setup, simulation, and results. And then over here on the right are four sets of results, two of which are not instantiated in the free download. And impedance is the first tab over here, and that's the one I'm going to be talking about in this video. So I've already run the default simulation for the program, which is an acrylic or plexiglass panel, 3 millimeters thick, clamped at all four edges, 23 centimeters wide, 35 centimeters tall, with a single DAEX19 CT4 exciter in the middle of the panel. So why is this the default simulation setup? Well, because I built this exact panel probably 3 years ago, and it's been sitting on the floor of my lab for years, and I use it to test the program. That's why. It doesn't necessarily sound particularly good, but it's what I use. So there you go. It's the default. So, okay, impedance is over here, and it's the electrical impedance of the exciter when attached to the panel. The reason why it's here is because it's something that you can measure using a variety of programs, and there are a lot of people who are measuring the impedance to get an idea of what is going on with their speaker setup. So, like, I use a thing called a Clio Pocket to do all of this, and I like it and it works really well, but they're kind of hard to buy in the US. So they're not easy to get. Room EQ Wizard can do this too. The Dayton Audio Test System DATS unit can do this, which used to be called the Woofer Tester, can do this too. So there's a variety of things that can make this measurement, and it's a fairly like pure measurement that's nice because it doesn't include room reflections and diffraction and all these crazy things that are hard to model and hard to understand what their effects are. So it's a more pure physical measurement without all the acoustic shenanigans going on. And for that reason, it actually tends to match up with the simulation pretty much perfectly if you built a setup that matches the simulation too. Whereas like room reflections and things will undoubtedly screw up these anechoic responses that I've been simulating. Okay, so here's our impedance, and there's a lot going on here. So let me do a different kind of simulation to simplify the results a little bit. I'm going to make this a 5 centimeter thick piece of acrylic rather than 3 millimeters thick. And something that I just realized, this is build 3 of 1.7, where I changed some things around and I changed some back-end code a little bit to fix one little tiny bug. Another thing that I fixed was there were some glitches happening at low frequencies because I was cutting out modes that weren't participating strongly in the response at low frequencies, and it didn't really affect anything, but it made things look weird. So I added some of those modes back in, and now the simulation gets mad, or the program gets mad at you if your simulation has fewer than 20 modes. And the error message is only going to come up if you have fewer than one mode. So at some point I need to go update that to say you have fewer than 20 modes. So this setup is going to have 25 modes, so it runs. I at first tried making it 10 centimeters thick, which only had 11 modes, and it didn't run. So I redid the video. Now it's 5 centimeters thick, and it runs. So if for some reason you are simulating something like this that only has 10 modes and it doesn't run right now, that's why, because I haven't updated the error message yet. It's always going to simulate a minimum of 20 modes, and it gets mad at you if you don't have 20 modes to simulate. And that avoids glitches at low frequencies, which probably doesn't mean anything to anybody other than me, because I'm the one writing the code and deciding how to speed it up. Okay, cool. So, okay, we've got a 5 centimeter thick chunk of acrylic that we've attached our exciter to, which more or less doesn't really move. I mean, it does move, but for all intents and purposes, it doesn't move. So it's like sticking it to a giant block of concrete, and this is the impedance that we get. So, okay, there's a couple things going on here. The impedance right here at low frequencies is due to the voice coil resistance. Then that rises over time because of the voice coil inductance. Okay, then we've got a resonant peak here that comes from the magnet mass moving. And then we have another peak up here that is still a little mysterious to me, but does show up in the measurements and is due to a coupling problem, from what I understand, between the voice coil plastic and the actual plastic that attaches to the plate. So eventually that plastic that attaches to the plate is going to start bending on its own, because it's just a plate of plastic too, and that first resonant frequency is up here. So even if we attach this to something pretty heavy, that is still going to bend on its own, and so we get a peak up here. And that's what I see in my experiments too, so kind of interesting. So there's no modes showing up in here because the impedance peaks due to the modes are proportional to the velocity of the mode. Up here at high frequencies, the velocities are pretty much non-existent relative to this impedance. Or the velocities are so small that we don't see anything due to them. So this is essentially the impedance of that exciter stuck to a giant block of concrete. Okay, let's now make this half a millimeter thick. This should get us to 1500 modes. So it's going to be a really thick, or sorry, really thin piece of acrylic that's essentially not even there. It's like just trying to drive air. So let's see, 1500 modes. Yep. Okay, this simulation is going to take a while, no doubt. So I'm going to put in my elevator music, and I'll be back when it's done. See ya. Cool. Okay, so now we have our results for the super thin acrylic panel. And so the impedance really just has a big peak up at like 700 hertz, and then there are a bunch of smaller peaks, which are the modes. This is, if I was somehow able to make the panel even thinner and thinner and thinner and thinner, this is the impedance peak due to the voice coil moving on its own of the exciter. So as the material gets thinner and thinner, the voice coil becomes the limiting factor in the movement of the panel, because it has the higher impedance relative to the actual panel. And then we don't even see the motion of the magnet hardly at all anymore. So the magnet probably isn't really moving at all because it's so much heavier than anything else in the whole system. And this is, first of all, this is not something that's actually probably going to work all that well. And why is that? Well, because the magnet is probably so heavy that it's just going to rip right off the panel. So if you support the magnet somehow, so that would be going back here and saying exciter magnet fixed, it'll probably work better. But, you know, I guess that's up to you to find out. So I usually try to aim for a decent amount of impedance matching, which means that I'm able to see peaks from the modes of the panel, and I'm also able to see the peak due to the exciter moving. And sometimes it can be hard to see the peak due to the exciter moving, but you'll know when the panel is so light and thin that you really only see the motion of the voice coil. It'll look like this. So you want to see something where the peaks are more spread out than this, probably. And that means that you have decent impedance matching going on. So, okay, one more thing to show, that if I plop multiple exciters on the panel, so here I'm going to move these around a little bit. So a few different types of exciters. I'll leave that one there. I'm going to move this one. And let's do one of these. And I'm going to set this back to 3 millimeters thick. Okay, so we're back to 512 modes, and we've got 4 exciters on the panel that are all being driven with 1 watt of power. We'll see that we can look at the impedance of each exciter individually. So I'm going to let this run, and then I'll look at the results when they're done. Wow, cool. Check that out. Kind of a weird response. So the exciters all definitely mess with each other at low frequencies and can cause some pretty interesting behavior. So like the negative impedance here relative to the DC impedance is when the exciter is trying to push on the panel, but the panel is pushing back because of the other exciters. And so you get like the opposite response of what you would expect right at that frequency for that exciter. So some weird things happen, for sure. And then their resonant frequencies change and all sorts of crazy stuff. So what's the blue one? Was that the... That was the 19CT4. Yeah, so that one doesn't have much impedance relative to these other ones. Cool. Yep, so that's the impedance of each exciter separately on the same panel. Pretty wacky response that you get here. It's actually not a terrible response, but I guess if you just cover a panel in exciters and drive them all, then you probably get something that's not that far away from piston behavior. So that's not super surprising, I suppose. Okay, cool. I'm approaching the end of the video series that I'm going to make for this version of PETTaLS, but there are still a couple left to make. So I'll see you in the next one. Thanks for watching. Bye.